So how is a Nerf basketball similar to a bowling ball, and how is it different? That's what we're going to be talking about today, and we're going to be dealing with the concept of density. Now, um, we probably have all experienced something that's made out of a Nerf. This Nerf material, real soft and spongy, and maybe we've been bowling as well. And we know that these two can be roughly the same size, and so we would say that they have the same volume. These two spheres have the same volume. But we also know that on one hand, a bowling ball is going to be a lot heavier than a Nerf ball. And so this brings us up to the idea of density. And so let's explore this a little bit more. Now, first off, density, a definition that we should definitely jot down, is the mass of an object divided by its volume. And so we have a formula here. We have density equals mass over volume, which we also sometimes like to just shorten off everything down and call it D equals M over V. Okay, so if this is our idea of density equals mass divided by volume, and we scroll back up here, the Nerf ball, we would say, and the bowling ball, let's pretend they both have the same volume. So what sets them apart is their mass. And the more mass you have, the greater your density if the volume stays the same, because the formula is D equals M over V. So if our volume is the same, the greater the mass, greater our mass is, the greater our density is. So we know that the bowling ball has a greater density because it has a greater mass than the Nerf ball that has a lesser mass. And really another way to look at it is if we were able to just zoom in and look at the atoms of each one of these, we would find out that there's lots of spaces, lots of empty spaces in the Nerf ball that are filled with air, and that's what gives that Nerf ball sort of the squishy feel, whereas the atoms in a bowling ball would be packed tightly together, and more atoms gives us more mass. So let's take a look at a sample problem involving density and see how we can attack it. Actually, before we do that, let's take a look at the units that we need to associate with density. So we have 3 units that are going to be associated with density. We've already talked about 2 of these 3 units. The unit for mass that we'll most often use is going to be grams. The units for volume we most often will use is milliliters, but we may also use centimeters cubed, depending. And then, of course, when you divide mass by volume, the units do not cancel. So our density unit will be grams per milliliter or grams per centimeter cubed, depending on which one of those we use. So let's do a sample problem here and see what we come up with. So it says calculate the density. Okay, so first off, we were being asked to calculate density. Okay, and that's important to identify. Calculate the density of an object that has a mass of 15 grams. Okay, so we know its mass is 15 grams, and it has a volume of 8.5 milliliters. So those are 3 pieces of information that are very important for this problem. So we're going to use the formula for density, D equals M over V, and because we are being asked to solve for density, we don't need to manipulate this equation whatsoever. We can plug values straight in. So 15 grams is our mass, and we're going to divide that by 8.5 milliliters. Now, we talked previously about significant figures, and the way it works for significant figures is we need to round to the least number of significant figures. So this value has 2 sig figs, and this value also has 2 sig figs. So it's going to make it easy on us. We're going to round our answer off to 2 sig figs. So 15 divided by 8.5 in the calculator, I get 1.7647058882. And so obviously that is way too many sig figs. We want to round this answer off to 2 sig figs. So let's round it off to 2 sig figs. So it's going to round off to 1.7. Now it would be 2 sig figs, but we have to look to the 3rd sig fig, and will it round the 7 up? And it does, because it's 5 or greater. So we're going to call it 1.8, and that's it. That's 2 sig figs. Now our units that we have to include are grams per milliliter, and that is the correct answer there. Okay, let's take a look at our next question here, and I'm going to actually change this question a little bit to make it, there we go. Okay, so it says let's take a look at it. It says, what mass in grams, so we're looking for mass, will a piece of gold have if it has a density of 19.8 grams per milliliter and a volume of 21 milliliters? Okay, so again, this is a density problem, but we are looking for mass. So we need to solve this equation for mass by isolating mass and making sure it's the numerator. So we're going to isolate this by multiplying both sides by volume. And then volume will cancel on this side, and we have now manipulated our equation so that it is solved for mass. So we can rewrite it as mass is equal to volume multiplied by density. So now we just need to plug our values in. So it told us that we have a density of 19.8. 19.8 grams per milliliter. We're going to multiply that value by 21 milliliters, which is our volume. And so this just becomes a multiplication problem. We're going to multiply these two values together. And so the milliliters and the milliliters cancel because we have a numerator and denominator. And let's do this. So we have 21 multiplied by 19.8. And so I get an answer of 415.8 grams. My question to you is, are we finished? And hopefully you should say, no, we're not finished, Mr. Camp, because this value here, this value for volume, has 2 sig figs. And this value here for density has 3 sig figs. And we need to round to the lowest number of sig figs. So we need to round this value off to 2 sig figs. So we're going to round 415.8 off to 2 sig figs. Now, one of the ways we could do this is we can just put it in scientific notation, make life easier on ourselves. So 415 rounded to 2 sig figs would be 4.2. We would round the 1 up because we have a 5, times 10 to the second grams, or we could call it 420 grams. Both of those answers would be correct if we rounded it off to 2 sig figs. And there we go. And so that's how we do density problems. Mass divided by volume. There's our formula.